Hello, and this is Dr. Ryan Johnson talking about section 2.2 for Introduction to Statistics. So here I've got kind of a split screen going on. I've got my worksheet right here on the right. I've got the reading that you did on the left. And so we're going to kind of connect how the worksheet connects to what you did in the reading. So in the reading, the main experiment was about rock, paper, scissors, and wondering if people who are new to rock, paper, scissors tend to not do scissors as much. And then here, the worksheet, this is a different study by Lunsford, Dowling, and Fink. And they were looking at, do people prefer bottled water compared to tap water? And so the first question is to state the research question. Make sure a research question should be a full sentence, complete sentence. And then identify the observational units. That's going to be similar to your reading when you identify the observational units there. And then the reading, you skip straight to the binary variable because you had this thing right here. And if you see here, with where the researchers with the rock, paper, scissors, they counted rock and paper and scissors, and that was kind of their first variable. And then they kind of changed to their variable there was gesture, right? And then they switched to a different variable, a binary variable that was scissors. Scissors or not. And so then that allowed them to combine two options into one. So in the same way, for number 3, identify the variable should match kind of like a gesture sort of thing, except in our study with bottled water. And then the binary variable should be something that helps break it into 2 that gets at the question. Okay, so then describe the parameter of interest and then follow the hint. So it should be a complete sentence starting with the parameter is the longer proportion of blah, blah, blah. Okay, it should relate to our particular situation here. One possibility here is that subjects have equal preference among all 4 waters. So we're essentially selecting one of the 4 cups at random. In this case, what is the long-run proportion, i.e. probability, that a subject in the study would select bottled water? That question is related to the setup. So reading that first paragraph about how the experiment is set up is important for answering that question. Now, we're restating an important definition here. So the null hypothesis is the by random chance alone explanation, and it's usually used for creating our simulation, our chance model. The alternative hypothesis is basically saying like an effect exists, like something's connected here. And it generally contradicts the null hypothesis, and so we usually use that's the wrong one. We usually use H0 for the null hypothesis and HA for the alternative hypothesis. And then for typing up your homework, I've got my computer upright, so it's harder to write. But basically, you don't have to have like the 0 as a subscript for your homework. You can just write H0 and HA. That'll be fine. Okay, now, so your answers to 6 and 7 should be the null and alternative hypothesis for the study, which is which. So one of those is there's nothing's going on, nothing's related. That's the null hypothesis. The other hypothesis should be like there's something going on. Okay, now, and this is the section where we kind of introduce some of the main symbols of what we're doing. And so one of the main symbols is pi, and instead of using, in high school, we might have used pi as 3.14. In statistics, it's always going to be the parameter. And so we'll tend to use Greek letters for the things we don't know and English letters for the things we do know. So pi is the proportion that we don't know. It's the parameter of like the whole world of like people who might drink water. And then the other symbol we've got is p hat. Okay, and so p hat is used to represent the proportion of successes. And so basically, why is there a hat there? Is because we have so many, we use the letter P so often in stats. We put a hat for this particular one, okay? So P hat is the proportion of our sample, okay? The P hat is the number we know, pi is the number we don't know. And so then 10 and 11 are just asking what P hat and N are in the study. Hypotheses are always conjectures about unknown parameter pi. You can also use H0 and HA as shorthand notation. A colon is used to represent the word is. So restate the null and alternative hypothesis using pi. So you can just use the symbols instead of the words like you did last time. Okay. So is the sample portion who selected bottled water in the study more than probabilities? Is the sample portion who selected bottled water in the study more than the probability specified in the null hypothesis? That's a yes or no question. Based on your null hypothesis should have a number in it, and the P hat should be a number. Compare them. Okay. So P hat is the sample portion, and then there's a pi for your null hypothesis. So compare them. Is it possible? For number 14, the key word is possible. Okay. And then, so here, we're going to do another simulation. So now remember how we have our 3S strategy. And so first we have statistic, and then we simulate, and then we look at the strength of evidence. So now we're thinking about, we've calculated the statistic, so now we're going to move towards simulating. Okay. Now, can we use a coin to represent the chance model specified null hypothesis like before? If not, can you suggest a different random device we could use? What needs to be different about our simulation this time? Okay, so explain why we cannot use a simple coin toss. Okay, so that should be related to the probability of when you flip a coin versus the probability we're dealing with here in this experiment. So we could do the simulation using a set of 4 playing cards, 1 black and 3 red. Explain how the simulation would work in this case. So for number 16, you should have complete sentences, and you should be setting up a simulation, which means you got to explain to me how you're doing randomness, how you're recording results, and how many times you're repeating it. And so that's some key things I'd be looking for in that simulation. Okay. Now, another way to do it is with spinners. So another option would be to use a spinner, like you would in playing a child's board game. So, or even an adult board game, because we can play board games too. So, explain how the simulation would work if you were using a spinner. In particular, what does each region represent? So tell me about the spinner. Tell me about like what fractions of the circle you're making, and then tell me like the smaller one and the bigger one, what do they represent? Okay, now, how many spins of the spinner will you need to do in order to simulate 1 repetition? So this should be related to the first paragraph because it's related to the sample size, okay? Okay, now, simulating with the applet. We'll now use the 1 proportion applet to conduct the simulation example. So if you've got this PDF on your computer, you can click the number 2 there, and it should take you to a website, or you can go follow Canvas to student resources, applets, 1 proportion. So I've got it pulled up already over here. And so then we're going to change this number. It's not going to be 0.5. I'm going to write in the wrong number. Okay, I'm putting in the wrong number. All right, and then I'm going to put in the wrong sample size. Okay, and the number of samples, 1,000 is usually pretty good. Okay, and so then I think I got ahead of myself there. Sample size, enter 1 for the number of samples. Oh, follow the directions, that's important. Report the number of successes, and so then draw samples. So now I'm doing a whole bunch of spinners. And we got I got 2 successes, which should be different from what you get. Okay. Okay. Now let's select the radio button, proportion of successes. Report the, let's do the proportion of successes. Report the proportion of success in the simulated. Your answer should be your answer to C to verify. Use your answer to C to verify how this value is calculated. So like to verify is like show me an equal sign of like your answer to part C, your answer to part D. What did you do algebraically that you can give me an equal sign, between those two things, right? Now, leaving the proportion of successes radio button selected, but unchecking animate. Unchecking animate. Click on draw samples 4 more times. Okay, so 1, 2, 3, 4. Okay. Do you get the same result each time? You shouldn't. You should get different results each time. Like some of them might be repeats. Like I got a repeat there. But you probably should get different results. Now, enter 995. Okay, and draw samples. So now I've done it 1,000 times basically. And so there's my probability distribution there. Okay. Comment on the center, variability, and shape of the resulting distribution. Okay, so center is going to be roughly where you can use, the center can be mean, median, or mode. Mean would be averaging all those things, which you could also just like click summary statistic right there. That would give you the mean. You could also say the mode, which one's most common. And then for the variability, you could give me that standard deviation right there, or you could say like most of the values are between here and here. That's fine. Either of those is fine. Okay, so that distribution is called the null distribution because it's created using the assumption of the null hypothesis. So recall the observed value of the sample's proportion, who selected bottle water in the study, was p hat equals 24/27, which is approximately 0.8 repeating. Looking at the null distribution you've simulated, is this a very likely result when the hypothesis is true? In other words, is this value far in the tail of the null distribution? So if I look at, I'm doing something totally different because I did a totally different wrong number. So, but now I can do it because we're here. So, because it's 7.5, 27, 1,000. Okay, so then there we get the null distribution, and then we're looking at like where does 0.8 repeating show up here? And so if I look at 0.8 repeating and on, I've got these guys and just these guys. So my question is this value far in the tail of the null distribution? It's so the tail would be like is when it gets really low. So this is in the tail, but not far in the tail. Okay, so the p-value, which is different from p hat, is estimated as the proportion of simulated statistics in the null distribution that are at least as extreme in the direction of alternate hypothesis as the value of the statistic actually observed in the research study. So remember our 3S strategy: statistic, simulate, strength of evidence. So the p hat was in step 1, statistic. Then we simulated, and then the strength of evidence is a p-value. So the p-value is measuring how weird is our statistic, okay? And so when it's really small, it's saying our statistic is unlikely, so it's weird. If it's not small, then it's saying it's not weird, okay? So here we have a little table that's a good starting point for p-values. So if your p-value is greater than 0.1, that means we're saying our sample could occur like anytime our sample is more likely than 1 in 10. And so it can happen, like 1 in 10 things happen all the time. So it's little to no evidence that something's going on. Whereas if the p-value is between 0.5 and 0.1, then it's kind of like our sample is in between like a 1 in 20 and a 1 in 10 scenario. And things that are in between 1 in 20 and 1 in 10, they happen all the time, but also they don't happen that often. So moderate evidence. Okay? And then if our p-value is between 0.01 and 0.05, then it's the difference between like a thing that happens like 1 out of 100 to 1 in 20, then that's getting pretty unlikely. Like if you're planning a picnic and it says the chance of rain is less than 5%, you feel good about planning your picnic, right? And then if the p-value is less than 0.01, so less than a 1 in 100 scenario, then you have very strong evidence. And so these two right here, I'm not doing that really, it's hard to draw this way. There we go. We'd often call those statistically, I'm just going to call it, it's hard to write, significant. So statistically significant is those two most of the time. Okay, there's other ways to like hedge one way or the other way depending on like if it's really costly to be wrong in one direction or the other, but that's often the standard one. Okay, so is the approximate p-value from a simulation small enough to provide much evidence against a null hypothesis? Okay, so I got a number. So you should remember this inequality right here. If you click on this in the app, you should have this inequality should be matching your alternative hypothesis. And so in this case, that's my alternative hypothesis would be using that inequality. And so then I'm counting then like how many things are as extreme or more as my sample. So my sample, I got a 0.8888 for my p hat, and so then I say the p-value then measures like how many other like simulated things are got that amount or more extreme in the direction of the alternative hypothesis. And so in this case, only 59 of 1,000. And so we're looking at a p-value then of 0.0590. Yours will be different because you're simulating with random numbers. And so yours should be a little bit different than mine. And so this example, this is a homework where you should be getting like moderate evidence here. And I think once in class, everyone got moderate, and then one person got strong evidence from their simulation. And if that's happening to you, just add another 0 there and draw more samples, and then you get a much closer to the real thing p-value. Okay? All right, do you consider the observed sample to be statistically significant? So does it fall in here? That's what we're kind of asking. And then suggest a new research question that you might investigate next, building on what we learned in this study. So that's up to you. Use full sentences and use some detail. Okay. Wait, I forgot to read number 24. How broadly are you willing to generalize your conclusions? Would you be willing to generalize your conclusions to water drinkers beyond the subject in the study? How broadly? Explain your reasoning. So this is where you go back to the experiment and use your common sense and say, does this experiment seem like it's getting at like all people? Or could it just be like a localized thing? And then ask some questions like, tap water might taste different in different localities, And so use your common sense and kind of come up with why or why not. This is you can generalize this to like all Americans, all people, you know. Okay, so then the next exercise has several parts, and is basically asking you to redo everything, but with the changing up what you call success and failure. And so if you change up what you call success and failure and then run it all again, you should hopefully end up with the same conclusion. And so, but your numbers will all be different. And so it's a good, this is a good exercise in doing all of that. And that really, you know, you'll be able to do that okay. Once you've done, if you've gotten up to this part, you'll be able to do all of this okay. So, all right, that ends my video for section 2.2.